Oh hi! Welcome to this bonus video on thermodynamics. And in this video I'm going to use the rules of thermodynamics to prove a very well-known and very important law of physics, namely the ideal gas law. Well, you probably know this law from either your high school physics or from your other courses or from other sources. The ideal gas law is a statement about a very dilute gas. If you take a gas and you put it in a box, in a volume, and you're going to measure the pressure of that gas, you multiply it with the space in which the gas is contained, in other words with the volume of the box, you get this product, and that product is equal to the temperature of the gas. There's a number in between, this part here, where N is a statement about how many particles are in the gas, and R is what we call the gas constant. Now, if we are going to take the amount of particles to be constant, so you don't add extra particles and the particles don't merge via chemistry into new particles, you're going to take N as a constant. In other words, the ideal gas law is given then by this relation. In physics, this thingy here means proportional to. P times V is proportional to V. There's a number in between, but the number is not very interesting for us right now, okay? Because it's a constant anyway. So this is the ideal gas law. Now, if you open up a book on thermodynamics or on gases, you probably will find this law, and they usually derive it too. But the way that it is derived is mostly based on microscopics. In other words, people then assume that the gas consists of particles that fly around, and every now and then a particle hits the container, so the edge of the box. That hitting, of course, is what we call the pressure. And if the box is big enough, then the particles take a little bit of time before they finally reach one of the edges, and that's a statement about the volume. So you know that the pressure and the volume should be related to each other, and then the temperature comes out. Now, that derivation is based on statistics. You take all the particles, you cannot track all the particles because there's billions and billions of them in there, but you can do statistics. You can say, if I know what the chances are of one particle hitting the side of the box, I can do the statistics of all these billion particles and take their average. And then if you do that exercise, you will find this law. Now, this derivation is based on microscopics. You have to assume, first of all, that the gas consists of particles. Secondly, that the particles can bounce. And if you really want to do it well, you also have to take into account how the particles are bouncing, how they feel each other, and whether they feel each other at all. So you have to make all kinds of microscopic assumptions. Now, obviously, we know that gases consist of particles, so that derivation that you find in the books based on microscopics is indeed correct. But you can also derive this law by making no microscopic assumptions at all. You can use just the laws of thermodynamics, and as you know, thermodynamics is a macroscopic theory. It just talks about the overall picture without knowing what's going on the small details. And it's that derivation that I would like to show you. Now, the upshot of that is going to be that once you have derived that law in that way, you have proven that this ideal gas law actually holds much more general than just for stuff that consists of bouncing particles. If I can prove this law without making assumptions of particles and whether they bounce or not and in what rate they do this, I've proven this law for all systems. So in that sense, the ideal gas law, you should actually be able to remove the word gas, because I'm going to show that the law applies to all kinds of stuff, even if they're not gases. I don't need the microscopic. Thermodynamics macroscopically will also give me that law, and that's what I would like to show you. Now, there's a second goal to this video, and that is to show you how one does the mathematics related to thermodynamics. And that part is abstract and technical, so please consider this video also as an introduction to how one does calculations using thermodynamics. Now, let's get started. Now, before we do so, let me just add a small extra piece about the history of the ideal gas law. The ideal gas law was already discovered in the 1600s and 1700s by experimentation. People in laboratories took gases, they made it dilute, so not too much gas in that box, and they just made measurements. They kept the constant fixed, right? They put a little fire underneath and they put the thermometer in there that checked that the gas was always at the same temperature, and then they started improving and expanding the box. And then they found indeed that if you make this bigger and this is constant, then P, the pressure, compensates. So originally this law was found by experimentation. Now later on, people, when they found thermodynamics, they could prove this in the thermodynamical way, and that's what I'm going to show you now. Alright, so let's get started. I'm going to remove this law because officially we don't know it at this point. I'm going to start with the first law of thermodynamics. And the first law, you will recall, is a statement about how you can change the energy of the stuff in the box. Now, be mindful, I'm going to call it stuff from now on, because I'm not going to make any assumptions on whether it's a gas or whether it's particles. It could be bananas in the box, it could be a liquid, it could be cats, it could even be something non-tangible. Something that you cannot pick up and touch and put somewhere else like you can with atoms or with molecules or with cats or bananas. And you have many of those systems in nature. For instance, if I put light in the box. Now light is some electromagnetic phenomenon, and yes, in quantum mechanics it's also sort of particles that are called photons, but light has very different properties than bouncing particles. For instance, light doesn't bounce against itself. So you can even have a box that you fill with light, and still what I'm going to show you is going to hold for that case. So that's quite interesting. In quantum mechanics, particles or stuff is not made out of particles, it is made out of, well, something that is called the wave function. And the wave function is a mathematical abstract concept that you cannot pick up and touch, but you can put it into a box. So you don't have to assume tangible objects even. So I'm going to say stuff in the box, and it's up to situation to tell you whether that stuff is light or actual tangible particles or some quantum mechanical exotic stuff. Okay, so I'm going to call it stuff. First law of thermodynamics. It says if you want to change the energy of the stuff inside, there's two things you can do. Either you start pushing and pulling on the stuff. That is called work, and we saw that work can be written as a change of the volume times the pressure. Or you can use the zeroth law and supply heat by a temperature difference. And heat, we saw, via the second law of thermodynamics, can be written as the temperature times this abstract thing called the entropy. So here's the first law. If you want to change the energy of the stuff in the box, you either have to push or pull on the thing, or you have to supply heat. And pushing and pulling means that you're changing the volume, and supplying heat means you're changing the entropy over here. Okay, that's the first law of thermodynamics. Now you might note that the thermodynamics here has more variables than there are equations. Let me explain what I mean. What I mean is, this statement is a statement about the energy, the volume, the entropy, the temperature and the pressure. So there's a lot of observables in that one equation, but you have only one equation. So you have 4 or 5 of variables relate to each other by one equation. Then mathematics tells you if you have more variables than you have equations, then these variables are not fully defined yet. Well, they are defined in concept, but their numbers cannot be fully defined. Compare this to the following situation. Suppose that in mathematics you have 12 equals x plus y. Okay? That's one equation with 2 unknowns, x and y. So you have more variables than you have an equation relating them. Now, what is the solution? Well, there's many of them. X plus y must equal 12, so x is 4 and y is 12 will work. X is 6, y is 6 will also work, and you have an enormous amount of possibilities for that. That's the same situation here. We have multiple variables, but you have only one equation relating them. This is just a statement that the first law of thermodynamics cannot tell you everything that you need to know about the situation you're looking at, our box with stuff in it in this case. You need to add a little bit extra. This is the strength of thermodynamics. Because you can still add a little bit of information about the situation at hand, that means this law will apply to many cases at once. So I have to supply some information about the stuff in the box. I'm going to make 2 assumptions. The first assumption is, whatever is in the box, the stuff, there's not a lot of it. So let's make it more rigorous. What I mean is that the density, it's not a P, it's a different symbol, it's the Greek letter R, the rho, and in physics we mean the density. It means how much stuff per cubic meter, and I'm going to say that that number is small. So if you want to think about a gas, I'm saying that's a dilute gas. There's not much of it in that box per unit volume. So that's one assumption. The second assumption I'm going to make is that the pressure of the stuff in the box, P, will go down, will become a smaller number if I increase the volume of the box. So that's what I mean here. P goes down when V goes up. Again, if you're thinking about a gas, that makes sense, right? Because if you make the box bigger and you're thinking about bouncing particles, well, if there's a bigger box, there's less probability of a particle finding its way all the way to the side of the box and bumping against it. And bumping against the side of the box is what we call the pressure. So a big box, you can expect to have a low pressure. Now again, I'm not saying that the stuff in here is bouncing particles. I'm just saying that whatever stuff is, it has this property. So it could be anything that has that property. It doesn't have to be a gas or particles. These are my assumptions. My claim now is the first law of thermodynamics, this relation with these assumptions about physics can fully specify how P, V and T are related, and we will see that that relationship is necessarily the ideal gas law. Okay, so let's get started. Now I'm going to start with this first assumption, that the density is a small number. That assumption has an immediate consequence, namely that the energy of the stuff in the box can only depend on the temperature. This assumption is going to say that the energy is only a temperature dependent function. If you have a box and you've put stuff in there, then that stuff in the box has at least a temperature, it has a volume and it has a pressure. So there's going to be three numbers. So you would expect the stuff in the box and their macroscopic properties like the energy to need three numbers, namely the volume, the temperature and the pressure. Now one of these is superfluous. You don't need the third one. Why? Well, because there's going to be some relationship that's going to relate those three numbers to each other. This could be the ideal gas law, yes? If you know P and you know V, then the number T is fixed. If you know the first two numbers, you can calculate the third. You can also take P and T and calculate the volume. Point here is, of the three numbers that make up the stuff in the box, you're only going to need two, because then the third one is fixed by whatever relationship holds them together. Now we're going to see that that relationship is the ideal gas law, but even if I don't know yet that it's the ideal gas law, I know there's going to be some law that's going to connect them together. Such a law, by the way, is called an equation of state in thermodynamics. So that means of the three numbers that describe the stuff in the box, I only need two of them. The third one is fixed by this equation of state, even if you don't know the equation of state yet. So of those three numbers, I just need two. I'm going to choose T and the volume. Okay, this statement is very general still. Now I'm going to put in this assumption, because I promised that under this assumption, this one, you actually lose the V dependence. And I'm going to show you that now. It's actually quite simple. You just have to look at the definition of the density. Density, by definition, means how much stuff is there per volume. So it's the amount of stuff per small amount of volume. Now, the amount of stuff is du. Because U is the energy, but if you know your relativity, then you know that energy is also related to mass and the properties of the stuff in the box. So if I say there's not much stuff in the box per unit volume, it's the same as saying there's not much energy in the box per unit volume. So my assumption simply means that this rho, which is du dv, is a small number. And by small, I mean approximately 0. So what I'm writing here is just this assumption made mathematical. That has a consequence, because if you look closely, you will see that it really says the derivative of the function u with respect to the volume is close to 0. Now you know from your basic high school physics that if a function has a derivative that is 0, then that function must be a constant. So u must be a constant as far as the volume is concerned. That's what we find here. In other words, if you would change the volume, the energy will not feel that change. The energy will not itself become bigger or smaller, even if you make the volume bigger or smaller. That's what this says, this derivative. But that means that u doesn't care about the value of v. In other words, that by good approximation, the energy is not v dependent. So that means it only has its t dependent left. It's at most temperature dependent. So we can immediately find from this first assumption that whatever the energy is, it can only depend on temperature and it cannot depend on the pressure. That is what comes from this first assumption. All right, that means the first assumption has been dealt with. Now, at this point, let me make a little mathematical sidestep. You might wonder why I called this a derivative. It looks like a derivative, it's du dv, but I write it like a fraction. And you might know, maybe you had a very strict mathematics teacher who told you that a derivative is not the same as a fraction. So here's my little mathematical side note. It's important to address this because I'm going to use this many times from now on. A derivative, which you typically would write as f with a prime, just means derivative, is defined as how much the function f changes divided by how much x changes. This is the definition of a derivative. Now note that this is actually a fraction. It just means number divided by another number. But the derivative definition has an additional part of its definition. It says, yes, a derivative is a fraction, but the numbers that you use to calculate this fraction have to be extremely small. That's given by this symbol here, limit dx goes to 0. So yes, a derivative is defined as a fraction, but under the additional definition that the thing that you're dividing over is extremely small. Dx goes to 0. That's the definition of a derivative. So, what's the difference between a fraction and a derivative? It's this limit thingy that you have to divide by small numbers. Now, go back to the first law of thermodynamics over here. Here it says du, a small difference, a small change in the function u. Here it says dv, a small change in the function v. Here it says ds, a small change in the function s. But the first law of thermodynamics implicitly says, well, these numbers are extremely small. It only holds for very small amounts of change of energy, volume, and density. So this guy, this limit taking, is already built into the first law of thermodynamics. This du, dv, and ds are already in the limit extremely small. So that's implicit. Everybody who does thermodynamics knows this, although nobody ever writes it fully down. But that means if you know that du, dv, and ds are already in this limit, then dividing du by dv, as we were doing here, is just the same as this derivative. It's really this fraction with already knowing that du and dv are extremely small numbers. So, I'm going to do in everything that's going to follow a lot of these ratios, and I'm going to divide du's by dv's and dp's by dt's and all these things I'm going to do in a moment. And those are ratios, fractions. But my point here is, yes, but because the numbers are already in the limit extremely small, those fractions are actually mathematically the same as derivatives. So that's what I also did here, right? I took this number, divided it by this number, and then I said, aha, that's a ratio, but because the numbers are small, it's really a derivative, and because the derivative is 0, u is a constant. So I'm going to constantly flip around between ratios and derivatives, and now I hope you have seen that in thermodynamics this is allowed. Small extra comment, that also means that all the rules that you know for derivative taking, like the product rule, are going to hold here as well. And I'm going to use some of those as we go along. Okay, so don't worry too much if you see me make fractions and treat them like derivatives. They are the same because I'm always working in the limit where numbers are very small. Okay, now having said that, I can continue. Again, we have shown that if the density is small by assumption, then the energy of the stuff in the box must necessarily only depend on the temperature. And that takes care of assumption number one. All right. Using this conclusion, I can do something fun with the first law of thermodynamics. Let me write it down. I'm just copying the law now. This is just me copy-pasting. Because look, if I now divide both sides of the equation by dv, and again that means I'm secretly taking the derivative with respect to v everywhere, I get this. Okay, still the same first law of thermodynamics. But we have concluded already that du dv is 0 because of the low density, so this is 0. That's 0. Over here I have the volume, and derivative with respect to volume, that's exactly equal to 1. So might as well remove this. And then what I end up with is that the pressure of the stuff in the box, according to the first law of thermodynamics, is given by the temperature times the derivative of the entropy with respect to V. So this is what I've now found. Now this doesn't quite help us, it seems at first glance, because, okay, the pressure is related to the entropy. The entropy is sort of a difficult thing. We don't have an entropy thermometer, so it's difficult to measure entropies, for instance. So it might be mathematically true, but what good does it do? Here's a beautiful piece of mathematics I'm going to put in. You can prove that the derivative of entropy with respect to volume is actually exactly the same as if you would have taken the derivative of the pressure with respect to the temperature. Let me write it down first. So ds dv is equal to the derivative of p with respect to t. So ds dv is the same as dp dt. If that's true, then that means ds dv can be replaced by dp dt. And then I end up with the following rule, that the pressure, I don't know what it is yet, but I do know that it should be the same as the temperature times the derivative of the pressure with respect to the temperature. Then I have this equation over here. I'm going to solve that in a moment, but first let me address this point, because all of a sudden I used here this strange rule. It's called a Maxwell relation. Some history. James Clerk Maxwell was a Scottish theoretical physicist in the 1800s who worked in his career on thermodynamics and on electrodynamics, and he's most well known for his work in electrodynamics. We find that the laws of electrodynamics, there's 4 laws of electric fields and magnetic fields, those are called the Maxwell equations. Maxwell was the guy who found exactly mathematically how electric fields and magnetic fields are related to each other, and we have beautiful courses on that in case you want to learn more about that. Now those are called the Maxwell equations, how electric fields and magnetic fields are related. It's a set of laws from electrodynamics. But in thermodynamics, the same guy, Maxwell, found special rules that are called the Maxwell relations. And those relations simply tell you that derivatives of all these numbers are related to derivatives of some of the other numbers. Now, I'm not going to prove this at this particular moment, because that is a story of its own, how one proves this. For the people interested, I'm going to do this at the end of this video as an encore. The only point that I want to make now is that this Maxwell relation is a purely mathematical result. I'm not putting in any physics when I use this Maxwell relation. It's completely fixed by just the laws of mathematics alone. Now that I'm going to show later. It's a little bit of a derivation. So for people interested, let me introduce that as an encore at the end of this video. For now, I'm going to accept it as fact. It is. And having used this, I have now ended up that the stuff in the box with the low density, there we go, has a pressure that is related to temperature in this particular way. note that this relation that we have found now doesn't contain any volumes anymore. All the volumes have been removed by this Maxwell relation. So ultimately, the equation that we found here is a relationship between the pressure and the temperature. And so that means we can find this relationship now. Now let's look at it for a bit. This is what we call this type of mathematical equation. We call a differential equation. Now what does that mean? Usually in mathematics you have exercises like this. 15 times x equals 7 plus x squared. Okay? There is some x that makes that equation work. You have to do the exercise and then you'll find the x, the number that makes it work. In case, this particular case actually has two numbers that make it work, but that's beside the point. The point here is that this is called an algebraic equation. An equation of which the solution, x, is some number. Here we have a differential equation. The outcome of this relationship is not a number p, it's a function p. Now what function is that? Well, it's a function that depends on temperature because the other thing appearing in the equation is the temperature. And you can see why this is, yes? It says there is some function, p, function of t, and if you take its derivative and you multiply it again with the temperature, you get back the function p of t. And the question now is, what is that function? How is p and t related such that if you take its derivative and multiply it with t, you get back the function itself? Now this is called a differential equation. Now you can study complete courses on solving differential equations. That's not my point here. So I'm just going to give you the solution and then we're going to check that the solution I'm giving you is actually correct. Okay? This differential equation gives you, so here's my this follows sign. It gives you that the pressure is a function of the temperature by linear relationship. It says that the pressure is just a temperature with some number in between. Let's call that number A. I don't know what it is. This is the solution of this differential equation. Now let's prove that that's the case. We can simply substitute. If this guy, this relationship between P and T is a solution to this differential equation, that means if we substitute this P into the equation, left side and right side should give you the same answer. Let's check. Let's put it into the right hand side first. It says take the derivative of your P with respect to T. Okay, that's easy. Just means you get the number A. Multiply it with T. Okay, then it becomes T times A. And that should be equal to the left hand side. And the left hand side, well, is A times T. So I get A times T equals T times A. That is the same. So my claim was correct. This really is the solution to this differential equation. Great. That means we have now half of the ideal gas law. Because the ideal gas law said that pressure and temperature are related in this linear way. That P equals T. The part is where the volume comes in. But if you recall, this is not a statement about volume, so we don't have the volume information yet. So that's the second half that we still have to go through. But it has shown us that P and T are linearly related, just as the ideal gas law tells us that they should. So this is half of the ideal gas law. Now, before we continue with getting the part, the volume part, let me just say that this A, this unknown number, is allowed to depend on V. It's a statement, this one, this differential equation, only on the T and P relation, so the number in between is still mathematically allowed to depend on the volume. So that unknown function as well of volume, I'm going to call, well, P with a little stripe on top, I'm going to call that P bar. It's just my symbol for the part, the volume part of my pressure. So this is my conclusion. All of this, the first assumption and the first law of thermodynamics, told us ultimately that pressure is times T, and is the volume part that I still have to look for. Here is half of my outcome. You can already see the ideal gas law coming out. Okay, good. There's a red box around it. I'm going to park this for now because I have to move on with the second half. And I'm going to remove all of this to make some space. There we go. And let's see if I can get the volume part out. Now note that I haven't used the second assumption yet, and it's the second assumption that will tell us the volume part. I'm going to start with the first law again, so let me copy it one more time. This is a copy paste of the first line over here, plus TDS. But now I'm going to do something sneaky. I'm going to write this first part as follows: minus dPV plus VdP, and then the TDS was still there, so I'm just going to copy that. Now what did I do? I replaced this part with that part. That's the same thing. It's mathematically the same. No physics was done in that step, it's just mathematics. How did I know that? Well, I used the product rule of differentiation. Remember that I made a comment before that if we work in the limit of extremely small du, dv and ds's, that my rules of differentiation hold here. Now you might remember from your high school physics or your other courses that if you take the derivative of a product, two functions f and g, and you take their combined derivative, that the product rule of differentiation tells you that that's the same as if you would have taken g times the derivative of f plus f times the derivative of g. So that's this. That's a product rule of differentiation. Okay, but I do have a product here, yes. I have the very smallness of a product, and we talked that the smallnesses come with the same rules as derivatives. So I can use the product rule on P times V, and if you work it out, then you will find you get minus PdV, that's the one that I had. I get another minus V dP, but that is cancelled by this one. So if I use the product rule on this thing, then you get back what I had originally. So it's really just the same thing. So no physics happened here, it's just a product rule differentiation that made me turn all of this into that. Okay, so it's mathematically true. But why did I do it? The reason that I did it is I want to end up with a relationship between P and V and then solve that, and then I get the V dependence of P. But in order to do so, I needed to get a dP in here somewhere. I didn't have a dP before, I just had a dV, so I used the product rule to turn it into a dP. You will see in a minute why this is useful. In fact, let me do it right now. I am going to take this equation, and just as before, I'm going to divide it by dV. So I get du dV equals minus dPV, it's a long expression, plus V dP dV plus T ds dV. This is just this rule divided by dV. Want to stress one more time, because dVs and du's and dP's are all very small numbers, then fractions, ratios, are just derivatives, so the same rules apply. In other words, this here, this fraction really is derivative, and we saw before that the energy only depends on temperature, and therefore the derivative with respect to the volume is 0. There we go. And I promised I would come back to the point of why I did this product rule trick. Notice that in my new expression, I now have a dPdV. I have somewhere built in here, in this term, how P and V are related. And that's what I wanted. I wanted P as a function of V. I want to investigate that. So I need something that says dPdV. And I just created that thing using my rule for differentiation. Okay, good. Let's move on. I have not used assumption number 2 yet, but here is where it comes into play. Look, I'm going to make a claim and then we're going to prove the claim. This guy, this term, is very small compared to that term. I will show this in a moment, but let me first tell you what my plan is, what my narrative is. If this number is very small compared to that number, and by small I mean really small, then for all practical purposes I can just remove this altogether. I can just throw it away. It's not really gone, as in the thing should be there, that's what the first law tells us, but by good approximation you might as well throw it away. So to make a comparison, suppose that I have 10,000 euros in my pocket, and somebody comes along and steals €1 from my pocket, then what I've lost is 1/100th of a percent. So if I say that I have €10,000 in my pocket, while it's really now 9,999, I'm only off by 1/100th of a percent. That's such a small difference. I'm not making too much of a mistake by still calling it 10,000. Okay, that's what we do here. As long as this really is smaller than that one, by very good approximation, I can throw it away. Now I have to prove that that is the case, so let me do that here. I'm going to look at each of these terms separately, so let me start with this one. dPV dV, I'm just going to write it out. Again, I can use the product rule. Then what I get is P plus V dP dV. So there we go. And this guy, I'm going to use this Maxwell relation that I had before. You recall I could use this Maxwell relation because it allows me to write a ds dv as a ds dv will become a dp dt. And again, in the encore I will prove that that Maxwell relation is mathematically correct. Now, I want to show that this part is bigger than that part. And in order to do that, I'm going to put in what I've already concluded, namely that how P and T are related. I could put that in. Let me do it here first. T times dP dt, but P is just this P bar times T, so the derivative will only work on this. So what I end up with is this T. This guy just becomes P bar. So I put this one here to calculate that derivative. Let's see what happens here. Well, this P again is P bar times T, so let's put that there. P bar times T. So that's that. Plus V times dP dV. I have to be careful now. I have to take the derivative of P with respect to V. Now the V part, the derivative, will only work on the P bar and not on the T. So the T goes in front and I get dP bar dV. There we go. So I've written out this term and I've written out that term. And now we'll do the comparison because my claim was that this is smaller than that. In other words, this must be smaller than that. And I will show that that's true in a moment. Now, first a small point. People might have noticed that when I wrote out this first term, I ignored the minus signs, right? There's a minus sign in front, I ignored it. Now, why did I do that? It doesn't really matter for my argument. If I go back to my 10,000 euros example, if I have 10,000 euros and somebody steals €1 from me, we talked about that it's still a very good approximation to call the number in my pocket 10,000, even though the real number is 9,999. Now somebody comes along when I had my 10,000 and gives me €1, then my new amount will be 10,001, which is also a very small number different than my original 10,000. It's just different in the other direction, but it's still only 1/100th of a percent in both directions. So the approximation that I'm looking for works in both directions, so it doesn't care whether you had a minus or a plus sign in front. So this is why I ignored the minus sign. Okay, now let's do the comparison. Note that this part and that part are the same. This number, whatever it is just T times P bar, but this is also T times P bar, so this is the same number. So if my claim is correct that this is smaller than that just means that this must be a negative number. And it is. Let me show you why. This number is negative. V is a positive number. Volumes come in positive numbers, yes? Temperature is also a positive number. Now, not in the Celsius scale, yes? You can have negative degrees on cold days in the winter, for instance, but the first law of thermodynamics assumes T to be measured in the Kelvin scale, and Kelvins start at T is 0. So I don't have to worry about T being negative because it's in the Kelvin scale, it is a positive number. So V times T in its totality is positive. But what about dP bar dV? Is that a negative number or a positive number? That's negative. By my second assumption. We have here that P bar goes down when V goes up. In other words, the function P should be should go down when the v goes up. Mathematically speaking, what I'm saying is that the derivative of p with respect to v is smaller than 0. That's just a mathematical restatement of this assumption. So that means in this particular case that v is positive, t is positive, but this derivative is negative by the second assumption. So this whole green part is negative. So going back to the comparison, this thing and that thing are the same, but this thing is smaller because you subtract a part. So it is a smaller number. Is it a lot smaller? Well, yes. If you make the volume very big, so you make the box in which you put your stuff very big, then v becomes a big number, so the amount that you are subtracting becomes very big indeed. So we have now found that indeed this guy is a lot smaller than that guy by the second assumption. It is negative because you subtract, that's the second assumption, and that it's a lot smaller is because of the first assumption, because the volume was very big compared to the stuff that was in there. So combination of first and second assumption tells me that the green part really subtracts a lot from this. And if you subtract a lot, then it means this must be an enormous amount smaller than that. And the bigger you make v, the more dilute you make your stuff or your gas, the better this approximation holds. All right. So what I now know is that by very good approximation, and it becomes better if you make the volume big, I can throw away this term. So I have now thrown it away. I don't need this anymore. So I'm going to remove that. And the remaining equation is then the following. I have v dp dv, let's put it on one side, equals minus t ds dv, but I'm going to use this Maxwell relation again. That tells me that it is this. So this first law under this assumption has now become this. Let's put in that I know that p is proportional to t. Then v dp becomes, the v only works on the p bar part, so the t goes in front, so I get d bar dv equals minus t. This derivative will now ignore the pv part. And there's a volume. So this is the law that I had where I plugged in my first conclusion, my first half conclusion. Then this relation has come out. I can do a little bit better still, because on both sides there's a t, and that means I can divide it away. So I can ignore this t and that t altogether. Now, somebody in mathematics will become worried now because you cannot divide a number away if the number is 0. Right? You cannot divide by 0, so if I divide the t away, I better make sure that t is not 0. But we don't have to worry about that. First of all, in the Kelvin scale, as we discussed before, t's are always positive numbers, so they're at least not negative. But could they be 0? No. The third law of thermodynamics says that you cannot go to absolute 0, so t will necessarily be bigger than 0, and that mathematically means you're free to divide it away. So what I've now found is, and I'm going to make a little bit of space, I'm going to write down the same equation here, a little bit cleaned up, that dp bar dv equals minus p over v. I think I've made a mistake because there's one v too many. Yes, I'm very sorry, this v was never there. It's my bad, my apologies. I just copy-pasted wrong from one line to the next in a slide a second ago. My apologies. So you can correct this for yourself. I just made a stupid copy-paste mistake. Long story short, when I went through the calculation, dp bar dv equals minus pv. And this again is what we call a differential equation. There's an unknown function, and that unknown function, and there's a bar too. So there's an unknown function, and the unknown function, if you take its derivative with respect to v, it should give you back the function itself minus divided by v. Okay, same as before, the outcome of this equation is not a number, P bar, it's a function itself. It's a function such that if you take its derivative, it gives back itself with a minus and a V down. Now you can puzzle on this yourself. I will just give you the solution. Then we're going to check that the solution is correct. P bar must then be some number, let's call it A, divided by V. Let's check that that's true. Let's just substitute it in the left-hand side first. If you take P bar's derivative with respect to V, you get A and then a minus over V squared. The minus is because of the derivative taking of a negative power. So left-hand side becomes minus A over V squared. Okay, let's check that that's the same as the right-hand side. P bar is A over V, and there's a minus sign in front and another V, so right-hand side also becomes minus A over V squared. So left is the same as right. In other words, this really is the solution. So what we have now is that the first assumption told me how P and temperature are related. P is proportional to temperature, and the second assumption told me that if the volume is big enough, that P is inversely related to the volume. And I can now put things together to get to my grand conclusion. Here's the grand conclusion. Take these two together. P, pressure, is a function of temperature, and V is given by P bar V, but P bar V is A over V, times T, then I get this. In other words, if I bring the V to the other side, P times V is some number, a number A, I don't know what that number is, times T. And that's the ideal gas law. That if you multiply the pressure of the stuff in the box times the volume which the stuff is contained, it's proportional to the temperature. And I got all of this just from the first law of thermodynamics and these two assumptions, and the rest was just pure mathematics, nothing else was there. Now I think that's extremely beautiful because, as I promised at the beginning of the video, that means that the ideal gas law is true even when there's no bouncing particles. All stuff, particles or no, that have these two properties obey the ideal gas law. So as far as I'm concerned, people should drop the gas there. They should call it the ideal stuff law because it holds for all that stuff. So I think that's extremely beautiful. By the way, that doesn't mean that the usual derivation with the bouncing particles and take the statistical average is wrong. That also gives you this. But it means that you've then only proved it for those bouncing particles, and now we see that it actually holds much more general. So that's an extremely nice conclusion. Now, you might have noticed that the ideal gas law, not ideal stuff law, but the ideal gas law had an extra number in between, namely some constant R, the gas constant, and N, the amount of stuff, the amount of particles in that box. I did not get that out, but that's to be expected because I left out the microscopics. So I never said that there was amounts of particles in there, so I cannot get out the amounts of particles. My thermodynamic doesn't know about the amounts of particles. And again, it should also hold when there's no particles around. So I could not get that number out, and that's not a drawback. It simply means that that number might be different if the stuff is not a gas, but the relationship is still the same. Now, to find that number, you have to do the experiment. Just put the stuff in the box, keep it at constant temperature, play around with the P's and the V's in the experiment, make the box bigger and smaller, see what P does, and you get the number out. So that's extremely nice. There we go. There's the ideal gas law as a macroscopic derivation. Now, to really round off this derivation, I still need to prove this Maxwell relation. At some point in this derivation, twice in fact, I used this Maxwell relation, and the Maxwell relation said that the following is true, that the derivative of the entropy with respect to the volume is the same as the derivative of the pressure with respect to the temperature. And I promise that that's a mathematical result that has very little to do with physics. And for an encore, let me show how that is done too. just to round off this derivation. So I'm going to remove this because this Maxwell relation that I'm now going to derive, is mathematical. It doesn't hinge on this particular example or the assumption that I made. It's an even more general rule, so I don't need the ideal gas law anymore, and I don't need this example anymore. I just need mathematics and mathematics alone. So here's my encore to prove this Maxwell relation. The power of mathematics. Now, I have to introduce a new function. The function is called A. Not to be confused, by the way, with the A that I had before that said unknown number. Just happen to pick the same symbol here. I'm going to introduce a new function that is called the Helmholtz energy. The Helmholtz energy is just energy, but written slightly differently. It's defined as the usual energy, U, minus temperature times entropy. This is by definition, so let me draw an equality sign with 3 bars. That means definition. There's no physics, there's not even mathematics, it's just me defining a new function. That function was first defined by Helmholtz, scientist from the 1800s. And Helmholtz did this for a reason that will become apparent in a moment. It turned out that some thermodynamical systems with energy in them are better described by the Helmholtz energy than by the usual energy because of mathematical properties. Sometimes it helps a situation if you can rewrite it into other variables that are easier to work with. And for some of those systems, the Helmholtz energy A is a better choice than the usual energy U. Okay, so let's see what we have here. I have the Helmholtz energy is the usual energy minus T times S. And I want to turn it into, again, the first law of thermodynamics, but now written in terms of the Helmholtz energy. And the first law always tells you how much energy changes, not what the energy is, A, but how much it changes, dA. So dA is what I now want to calculate, given my definition for A. And well, it just means take the small amount of U minus Ts. Well, that just means du, a small amount of U, and the small amount of T times S. And remember now that I said before that if you work with smallnesses on the scale that we are in thermodynamics, then these sorts of rules play by the same rules as your usual derivatives. So I have the smallness of Ts, and I can use the product rule of differentiation again, which gives me T times ds minus S times dt. Okay, now let's continue. Du, I know from the first law of thermodynamics. So I can replace du, but what I know from the first law it should be. So du I will now replace by minus pdv plus tds. So this is just that by the first law. And then there's all this other stuff, minus tds, minus sdt. And what you immediately see then is that this TDS that comes from here and the minus TDS that came from the product rule are going to cancel each other out. And that's because Helmholtz, the scientist, wanted that to happen. Because look what we have now. We now have that the small change in the Helmholtz energy is given by minus PdV, that's just the work, and minus SDT. So this is the first law of thermodynamics, but written in Helmholtz energy. And Helmholtz was happy with this result. Because if you now want to calculate the change of the Helmholtz energy, you just need to change in volume dV, and that's easy to measure, right? You just put your ruler next to your container and see how much it expands. So dV is an easy to measure number. And you need the change in temperature. But temperature is also easy to measure by the 0th law of thermodynamics. So the nice thing about the Helmholtz energy is that its change is expressed in easy to measure volumes and temperatures. And that was not the case with the energy, the original energy written in entropies. If you wanted to calculate it or to measure it, you needed to measure the entropy changes, ds. And it's very difficult to measure changes in entropy. We don't have an entropy meter. So Helmholtz defined this new energy such that its change contains the same information as the original first law of thermodynamics, but just in a way, just expressed in things that are easier to measure than the original version. So this is the Helmholtz energy and the first law. So I'm going to replace all this because I'm now going to work with the Helmholtz energy to ultimately prove the Maxwell relation. So all of this was just introduction to the Helmholtz energy. If you want to be very pedantic about it, it's called the Helmholtz free energy if you look it up in the books. So I'm just going to copy paste it so I have some space left. I see that I'm running out of ink, so I will continue in blue. dA equals minus PdV plus, minus SdT. I want to express one more time, there's no new physics here. It's still the first law of thermodynamics, just written in a new type of energy. There was no physics removed from it, there's no physics added to it, it's just the same physics in a different mathematical form. Okay, here is the Helmholtz energy, its change, so the first law in terms of Helmholtz energy. Alright, let's play around with this a little bit. As we saw before, a system consists of three numbers that you need to measure: the pressure, the temperature and the volume. Now which of those numbers you take, which two, doesn't matter, the third one is fixed by the other two, so you get to make a choice. And I am going to say that it depends on T and V, and then pressure is fixed by whatever relation, whatever equation of state, ideal gas law for instance. Alright, now let's make a mathematical statement. If I just know, so suppose I didn't know this physics part, I just know the mathematics part, I just know that it depends on T and V. If I, from this relation, try to get the smallness, dA, then I can use yet again a rule from differentiation. In differentiation you have, derivative taking, you have the chain rule that says that if you take a derivative of something with respect to T and to V, you are to use the chain rule, which says, well, dA is the same as dA dV dV. This is a chain rule. But since you have two parameters here, you use the chain rule twice, once for the V part and once for the T part. So I know from derivative taking, just pure mathematics alone, that my small amount of change of the Helmholtz energy is the same as what the chain rule tells me that it should be. So I have two versions now of the same expression. I have the one that comes from physics, the first law of thermodynamics, so that's the physics expression for the change of Helmholtz energy. And I have the mathematics expression, which comes from the chain rule. But these two things have to be the same. This has to be the same as that. And that comes with the conclusion. If I want this dA to give me the same number as that dA, then it means the right hand side of both must be equal to each other. And that means that the part in front of the dV's, so that will be this thing and that thing, that those have to be the same. So minus P should be the same as dA dV. This is just me reading off that if dA has to be the same as this dA, then the number in front of the dV's, minus P and dA dV, have to be the same number. That's the only way that I can make these two be the same, make them match. But there's more, because the parts in front of the dT's also have to be the same, because otherwise dA is not equal to dA. So I have another relationship that I can get from this. Minus S should be the same as dA dt. So I get two special relationships here, just from mathematics and the first law alone. We're almost at the Maxwell relation, but I cannot help myself and make a small comment here. S was introduced as the amount of energy that cannot be used to perform work. But as I said before, there's no entropy meter, so how does one measure that number? And here you have a way to measure it. Because the only thing you have to do is you have to take the Helmholtz energy, and the Helmholtz energy, as we saw before, is ultimately measured by changes in temperature, which is easy to measure, and changes in volume, which is also easy to measure. So I can very easily measure the Helmholtz energy. I just need volume and temperature, which are easy. And this relationship that we found now is that if you have your function for A, again easy to measure, and you take its derivative with respect to T, you get the entropy. So it's pretty cool. All of a sudden, using these relationships, one can now measure entropies simply by measuring volumes and temperature changes. So if you ever worry about, well, how do I get the number for entropy from an experiment, use the Helmholtz energy, it will get you there. So that's what this beautiful relationship tells you. Again, I said we're almost at the Maxwell relation that I set out to prove. I just have to do one more step. I have a derivative of A with respect to V, and here I have a derivative of A with respect to T. Now what if I take this relationship and take its derivative with respect to T? There is already one with V. Let's put another one there with respect to T. So I'm going to keep these separated for a moment. So I'm going to take whatever came out here, I'm going to take its derivative with respect to T. But what I do on the left hand side, I also have to do on the right hand side. So I get minus dp dt, so I also have to take the derivative of t with this, at the right hand side. Okay, then I have this, fine. Let's move on here. Here I have the derivative with respect to t, and I'm going to put another derivative in front of it with respect to v. So let's do that. I'm going to put another derivative in front of there with respect to v. There you go. But what I did on the left hand side, I should also do on the right hand side. So the other side should also have its derivative taken with respect to v. There we go. So I get again two equations. Here's the beautiful part. Here's the mathematical part. I have two derivatives here of the Helmholtz function. One's with respect to v and one's with respect to t. But I have the same here. One's with respect to t, one's with respect to v. But I do them in different orders. Here I first take the v derivative and then take the t. Here I first do the t and then the v. But mathematics tells us, the rules of differentiation tells us that if you take two derivatives, it doesn't matter in which order you do them. You can take first the x derivative and then the y derivative, or first the y derivative and then the x derivative. The order doesn't matter, the outcome is going to be the same. It has nothing to do with physics, that's just mathematics alone. But if that's true, and it is, then that means this guy is the same as that guy. So the left-hand sides of these two equations are the same, but then the right-hand sides also must be the same. So this guy then must be the same as that guy. Let's combine that. Let's write it in its own little separate equation. This mathematical conclusion thus tells us that ds dv is equal to dp dt. I dropped the minus signs, by the way, because it appears on both sides. And this guy over here, that's the Maxwell relation. That's the one that I used in my bigger derivation of the ideal gas law. So what I promised, I hope I've now shown you that the Maxwell relation here is a mathematical result that holds for all systems in thermodynamics, and I've now proven that purely mathematically. So that step that I did in the derivation of the ideal gas law had nothing to do with the fact that I had a particular box with stuff in there and it had assumption number 1 and assumption 2. None of that. Just mathematics and the first law of thermodynamics. So feel free to use this rule in any system that you care to use in thermodynamics. It will always work. So that concludes everything. I think I've filled in all the gaps. We have now proven the ideal gas law simply by taking the first law of thermodynamics, not making microscopic assumptions, not doing measurements, just the first law of thermodynamics. Two assumptions on the diluteness of the stuff and that this pressure goes down as the volume goes up, and the rest was just mathematics. So I hope that has hammered home the point how useful thermodynamics is. Once you know your thermodynamics and your mathematical steps, then you just have to sprinkle small amounts of physics over it, and you don't need the microscopics. The sprinkling of the extra physics on it will give you all the laws that you might be interested in. And that's the beauty of thermodynamics. It really is beautiful.